Did you know that time can slow down or speed up depending on where you are in the universe? This isn't science fiction, it's the reality of space-time, the fabric that weaves together the cosmos. From the way gravity bends time near massive objects to the mind-bending effects of traveling at near light speeds, space-time is full of surprises that defy our everyday experiences. In this video, we're diving into 30 astonishing facts about space-time, each one more fascinating than the last. You'll discover how black holes warp reality, why time might not flow the way we think it does, and what happens when the rules of physics seem to break down. By the end, your understanding of reality might just be turned upside down. And to kick things off, here's a teaser. What if I told you that time itself could come to a standstill under the right conditions? Stick around, this is just the beginning. Imagine the universe as a giant, stretchy sheet of fabric that holds everything together. This isn't just a metaphor, it's the foundation of Einstein's theory of general relativity. According to Einstein, space and time aren't separate entities but are woven together into a single, four-dimensional fabric called space-time. Think of it like a trampoline. When you place a bowling ball on it, the trampoline stretches and curves under the weight. In the same way, massive objects like stars and planets warp the fabric of space-time, creating dips and curves. These distortions are what we experience as gravity. The deeper the curve, the stronger the gravitational pull. But here's where it gets even more fascinating. This warping doesn't just affect space, it also bends time. Near a massive object, time actually slows down compared to areas with less gravity. It's as if the universe itself is playing tricks on our perception of reality. And this is just the tip of the cosmic iceberg. What happens when the fabric of space-time is stretched to its limits? Well, that's where things get truly mind-bending. Now, let's talk about something that sounds like it's straight out of a sci-fi movie, but is very much real: time dilation. This is the mind-bending phenomenon where time doesn't tick at the same rate everywhere in the universe. Near massive objects or when traveling at incredibly high speeds, time actually slows down. It's not just a theoretical idea, it's been proven. Take GPS satellites, for example. These satellites orbit Earth at high speeds and experience weaker gravity compared to the surface. Because of this, the atomic clocks on board actually run faster than those on Earth. If scientists didn't account for this difference, your GPS would be off by several miles in just a day. That's how real and measurable time dilation is. But what if we take this to the extreme? Imagine living near a black hole, one of the most massive and mysterious objects in the universe. The gravitational pull of a black hole is so intense that it warps space-time to an extreme degree. If you were to hover near the edge of a black hole, what scientists call the event horizon, time for you would slow down dramatically compared to someone far away. To an outside observer, it might look like you're frozen in time, barely moving, while for you, time would feel normal. It's a bizarre and fascinating thought experiment that shows just how strange the universe can be. And speaking of black holes, they don't just warp time, they stretch the very fabric of space-time to its limits. But what happens when space-time is stretched too far? That's where things get even more extreme, and it leads us to our next mind-blowing fact. Black holes are the ultimate cosmic heavyweights, bending the rules of space-time in ways that seem almost impossible to grasp. Picture a black hole as a cosmic vacuum cleaner, but instead of sucking up dust, it warps the very fabric of reality. The gravitational pull of a black hole is so immense that it creates a deep, inescapable well in space-time. This distortion is so extreme that not even light can escape once it crosses a certain point known as the event horizon. Think of the event horizon as the point of no return, like the edge of a waterfall. Once you go over, there's no coming back. Now, here's where it gets truly mind-bending. If you were to watch an object fall into a black hole, something strange would happen from your perspective. As the object approaches the event horizon, time for that object would appear to slow down, almost as if it's frozen in place to you, the observer. It might look like the object is hovering forever at the edge, never quite crossing over. But for the object itself, time would feel normal. It would just keep falling, unaware of the cosmic drama unfolding from your point of view. This bizarre effect is a direct consequence of how black holes stretch space-time to its absolute limits. But what if we push this idea even further? Could the extreme curvature of space-time around a black hole create something even more extraordinary? This brings us to the tantalizing concept of wormholes, theoretical tunnels through space-time that could connect distant parts of the universe. While wormholes remain speculative, they're a fascinating possibility born from the same extreme conditions that black holes create. Imagine folding a piece of paper so that two distant points touch. That's essentially what a wormhole would do, creating a shortcut through the fabric of space-time. It's a concept that blurs the line between science and science fiction, and it all starts with the incredible power of black holes to warp reality. What if you could step through a cosmic doorway and emerge on the other side of the universe in an instant? This isn't just the stuff of science fiction, it's the tantalizing idea behind wormholes. Predicted by Einstein's equations of general relativity, wormholes are theoretical tunnels through the fabric of space-time that could connect two distant points in the universe. Think of it like folding a piece of paper so that two far apart dots touch. Instead of traveling the long way across the paper, you could punch a hole straight through, creating a shortcut. In theory, a wormhole would work the same way, bending space-time so dramatically that it creates a bridge between two locations that would otherwise be impossibly far apart. But here's the catch: while wormholes are mathematically possible, we've never observed one in the universe. They remain one of the most intriguing what-ifs in physics. To exist, a wormhole would require an immense amount of energy and a type of exotic matter with negative energy density, something we've yet to discover. Without this exotic matter, the wormhole would collapse instantly, making it impossible to traverse. Even if we could stabilize one, the journey through a wormhole would be fraught with challenges. The intense gravitational forces could tear apart anything that tried to pass through, and the stability of the tunnel itself is still a mystery. So, could we ever use wormholes to travel across the universe? The answer, for now, is a cautious maybe. While the idea is thrilling, the practical hurdles are enormous, but that doesn't mean scientists aren't exploring the possibilities. Some researchers believe that wormholes might be connected to the strange world of quantum mechanics, where particles can seemingly teleport or exist in multiple states at once. Could the key to unlocking wormholes lie in the quantum realm? It's a question that bridges the gap between the very large and the very small, hinting at the profound mysteries that still surround space-time. And speaking of quantum mechanics, it's time to dive into how the tiniest particles in the universe might hold the secrets to the biggest cosmic puzzles. When we zoom in on the universe to its smallest scales, the rules of space-time start to break down in ways that even Einstein couldn't have imagined. At the quantum level, the smooth, continuous fabric of space-time that general relativity describes begins to look more like a frothy, chaotic sea. This is the strange world of quantum foam, a concept that suggests space-time might not be smooth at all, but instead made up of tiny, fluctuating bubbles or grains. These bubbles are unimaginably small, on the scale of the Planck length, which is about 1/trillionth of a trillionth of the width of a human hair. At this scale, the very fabric of reality becomes unpredictable, with particles popping in and out of existence and space-time itself fluctuating wildly. This granular nature of space-time challenges Einstein's elegant model of a smooth, continuous fabric. Instead of a calm, unbroken surface, quantum mechanics paints a picture of a turbulent, ever-changing landscape. It's as if the universe has a hidden layer of chaos beneath its serene exterior. This idea isn't just theoretical, it has real implications for how we understand gravity, particles, and even the origins of the universe. For example, some scientists believe that quantum foam could help explain the behavior of black holes or the mysterious nature of dark energy. But for now, it remains one of the most profound mysteries in physics, a reminder that the deeper we look, the stranger the universe becomes. And speaking of mysteries, this granular view of space-time also raises questions about the speed of light, a fundamental constant that plays a crucial role in shaping our understanding of the cosmos. What happens when we push the boundaries of light speed, and how does it interact with the fabric of space-time? That's where our next mind-bending fact takes us. The speed of light isn't just fast, it's the ultimate speed limit of the universe. Clocking in at about 300,000 kilometers per second, light moves so quickly that it could circle the Earth 7.5 times in just 1 second. But here's the kicker, this speed isn't just a random number. It's a fundamental constant woven into the very fabric of space-time, shaping how we understand everything from the smallest particles to the largest galaxies. According to Einstein's theory of relativity, nothing in the universe can travel faster than light. Not spaceships, not information, not even gravity itself. This cosmic speed limit isn't just a rule, it's a cornerstone of reality. Why is light speed so special? It all comes down to causality, the idea that cause must come before effect. If something could travel faster than light, it would break this fundamental principle. Imagine sending a message faster than light. It could arrive before you even sent it, creating a paradox that would unravel the logical structure of the universe. This is why the speed of light isn't just a limit, it's a safeguard that keeps the universe running smoothly. Even something as simple as communicating with a rover on Mars highlights this. When NASA sends a signal to the Curiosity rover, it takes about 20 minutes to reach Mars because of the vast distance. If we could send that signal faster than light, we'd be bending the rules of causality, and the universe simply doesn't allow that. But the speed of light does more than just enforce cosmic rules. It also defines the structure of space-time itself. In Einstein's theory, space and time are intertwined, and the speed of light acts as the glue that holds them together. This relationship is captured by something called the space-time interval, a measure that combines space and time into a single, unified concept. Think of it like this. No matter where you are in the universe, the space-time interval between two events remains constant, even if observers in different locations measure different distances or times. It's a bit like saying that while two people might see a painting from different angles, the painting itself doesn't change. The speed of light ensures that this cosmic consistency holds true, no matter how fast you're moving or where you are in the universe. So, what happens when we try to push the boundaries of this cosmic speed limit? That's where things get even more fascinating, and it leads us to the next mind-bending concept, space-time intervals and how they shape our understanding of the universe. Let's dive into one of the most fascinating aspects of space-time, the idea that space-time intervals are invariant. This might sound like a mouthful, but it's a concept that lies at the heart of Einstein's theory of relativity. Imagine two events happening in the universe, say, a firework exploding on Earth and a star going supernova in a distant galaxy. To someone standing on Earth, these events might seem to happen at different times and places. But here's the twist. No matter where you are in the universe or how fast you're moving, the space-time interval between those two events stays exactly the same. It's like a cosmic rule that ensures everyone, no matter their perspective, agrees on the fundamental relationship between space and time. To break it down, think of space-time as a four-dimensional grid where every event has a specific location in both space and time. The space-time interval is a way of measuring the distance between two events, combining both their spatial separation and the time that passes between them. What's remarkable is that this interval doesn't change, even if observers are moving at different speeds or in different directions. For example, If you're on a spaceship traveling near the speed of light, you might measure the distance between two events differently than someone on Earth. But when you factor in both space and time, the space-time interval remains constant. It's a bit like two people looking at the same mountain from different angles. They might see different slopes, but the mountain itself doesn't change. This invariance isn't just a neat mathematical trick. It's a cornerstone of how we understand the universe. It ensures that the laws of physics work the same way for everyone, no matter how they're moving. Without this principle, the universe would be a chaotic place where cause and effect could get tangled up. But because space-time intervals are invariant, we can trust that the universe operates in a consistent, predictable way. This idea also helps explain why the speed of light is so fundamental. It's the one constant that ties space and time together, ensuring that the fabric of reality remains coherent. So, what does this mean for our understanding of the cosmos? It's a reminder that space and time aren't separate entities but are deeply intertwined, forming a single, unified structure. This interconnectedness shapes everything from the motion of planets to the behavior of light, and it's a key part of why the universe works the way it does. And as we explore further, we'll see how this principle leads to even more mind-bending ideas, like the possibility of time travel and the nature of black holes. But for now, let's take a moment to appreciate the elegance of space-time intervals, a cosmic constant that keeps the universe in harmony. Let's explore one of the most famous thought experiments in physics, the twin paradox. Picture this: you have identical twins. Let's call them Alex and Jamie. Alex decides to embark on a space mission, traveling at nearly the speed of light to a distant star and back, while Jamie stays on Earth. When Alex returns, something astonishing happens. Despite being the same age when they parted, Alex is now younger than Jamie. How is this possible? It all comes down to the relativity of time, a cornerstone of Einstein's theory of special relativity. Here's the key idea: time isn't absolute. It flows differently depending on how fast you're moving. For Alex, traveling at near light speed, time slows down relative to Jamie, who's stationary on Earth. This isn't just a trick of perception, it's a real, measurable effect. Think of it like two clocks ticking at different rates. Alex's clock, moving incredibly fast, ticks slower compared to Jamie's. When Alex returns, less time has passed for them than for Jamie, making Alex biologically younger. It's a mind-bending concept, but it's been confirmed by experiments with atomic clocks on fast-moving jets and satellites. Time really is relative, and the twin paradox is the perfect illustration of this strange but true phenomenon. To make this even more relatable, imagine you're on a train moving at an incredibly high speed. From your perspective, everything inside the train feels normal, but to someone standing on the platform, your watch would appear to tick slower. The faster you go, the more pronounced this effect becomes. It's not just about clocks, it's about how time itself bends and stretches depending on motion. This is why the twin paradox isn't just a theoretical curiosity, it's a profound insight into the nature of reality. Now here's where it gets even more intriguing. The twin paradox isn't just about time slowing down, it's also about the symmetry of motion. From Alex's perspective, it might seem like Jamie is the one moving away at near light speed, so shouldn't Jamie be the one who ages slower? The resolution lies in the fact that Alex's journey involves acceleration and deceleration, breaking the symmetry. This subtle difference is what makes the paradox work, showing that time dilation isn't just about speed but also about changes in motion. So, what does this mean for our understanding of the universe? It's a reminder that time isn't a fixed, universal constant. It's flexible, shaped by motion and gravity, and full of surprises. And as we'll see next, this flexibility isn't just limited to time. It extends to the very fabric of space itself, as the universe continues to expand in ways that challenge our imagination. Now, let's shift our focus to one of the most groundbreaking discoveries in modern astronomy, the expanding universe. For centuries, people thought the universe was static, unchanging, and eternal. But in the early 20th century, something extraordinary happened. Astronomers like Edwin Hubble observed that distant galaxies weren't just sitting still, they were moving away from us. And not only that, the farther away a galaxy was, the faster it seemed to be receding. This observation turned our understanding of the cosmos upside down. The universe wasn't static after all. It was growing, stretching the very fabric of space-time as it expanded. Think of space-time as a loaf of raisin bread baking in the oven. As the dough rises, the raisins representing galaxies move farther apart. It's not that the raisins are traveling through the dough itself is expanding, carrying the raisins along with it. In the same way, galaxies aren't just drifting through space. Space itself is stretching, pulling them apart. This expansion isn't limited to a few galaxies, it's happening everywhere on a cosmic scale. Every point in the universe is moving away from every other point, like dots on the surface of an inflating balloon. But here's where it gets even more fascinating. This expansion isn't slowing down, it's speeding up. Scientists call the mysterious force driving this acceleration dark energy. We don't yet know exactly what dark energy is, but we do know it makes up about 68% of the universe. It's like an invisible hand pushing galaxies apart faster and faster, stretching space-time in ways we're still trying to understand. This discovery has profound implications for the future of the universe. If dark energy continues to dominate, the expansion could eventually pull galaxies so far apart that the night sky would grow darker and emptier over billions of years. So, what does this mean for space-time itself? As the universe expands, the fabric of space-time stretches, altering the distances between objects and even the way time flows on cosmic scales. It's a reminder that space-time isn't a fixed stage, it's dynamic, constantly changing, and full of surprises. And as we'll see next, this stretching of space-time isn't just a distant phenomenon. It's happening right here, right now, shaping the universe in ways we're only beginning to comprehend. Now, let's turn our attention to one of the greatest mysteries in modern cosmology, dark energy. This invisible force is not only shaping the universe but also accelerating its expansion. Imagine the universe as a balloon being blown up faster and faster, with galaxies drifting apart at an ever-increasing speed. That's exactly what dark energy is doing, stretching the fabric of space-time itself. Scientists first discovered this phenomenon in the late 1990s when they observed that distant supernovae were dimmer than expected, indicating that the universe wasn't just expanding, it was speeding up. This revelation was so shocking that it earned the researchers a Nobel Prize, and it completely changed our understanding of the cosmos. So, what exactly is dark energy? The truth is, we don't fully know. It's invisible, doesn't interact with light, and seems to permeate all of space. What we do know is that it makes up about 68% of the universe, dwarfing everything else, including stars, planets, and even dark matter. One leading theory suggests that dark energy is a property of space itself, often referred to as the cosmological constant. This idea dates back to Einstein, who initially proposed it to explain a static universe, a concept he later abandoned. Ironically, it turns out his idea might have been right, just for the wrong reasons. Instead of keeping the universe static, the cosmological constant appears to be driving its accelerated expansion. The implications of dark energy are profound. If this acceleration continues, the universe could face a future where galaxies are stretched so far apart that they become invisible to one another. Over billions of years, the night sky could grow darker and emptier, with only a handful of nearby galaxies remaining visible. It's a chilling thought, but it also highlights just how dynamic and unpredictable the universe can be. Dark energy reminds us that space-time isn't a fixed backdrop. It's an active participant in the cosmic drama, constantly reshaping the universe in ways we're still struggling to understand. But dark energy isn't just about the future, it's also a window into the past. Its existence raises questions about the very beginning of the universe and the forces that set everything in motion. Which brings us to the next mind-blowing fact, the Big Bang, the explosive event that gave birth to space-time itself. How did it all begin, and what does it mean for the fabric of reality? Let's dive into the origins of the universe and uncover the story of how space-time came to be. Let's rewind the cosmic clock to the very beginning, the Big Bang. This wasn't just an explosion in space, it was the birth of space-time itself. Before the Big Bang, there was no before. Time, as we understand it, didn't exist. The universe wasn't expanding into anything because there was no outside to expand into. Instead, the Big Bang marked the moment when space and time burst into existence, creating the stage on which everything, stars, galaxies, and even us, would eventually play out. It's a concept that stretches the limits of our imagination, but it's also the foundation of modern cosmology. At the heart of the Big Bang lies a mind-bending idea, the singularity. This is the point where all the matter, energy, and space-time of the universe were compressed into an infinitely dense, infinitely small point. To put it simply, the singularity is where the rules of physics as we know them break down. Gravity becomes so intense that even space and time lose their meaning. It's like trying to divide by zero. Our equations just can't handle it. This is why the Big Bang isn't just a scientific theory. It's a profound mystery that challenges our understanding of reality itself. But here's where it gets even more fascinating. In the first fraction of a second after the Big Bang, something extraordinary happened: cosmic inflation. Imagine the universe expanding faster than the speed of light, doubling in size over and over again in the blink of an eye. This rapid expansion wasn't just a burst of energy, it was the stretching of space-time itself, smoothing out the universe and setting the stage for everything that followed. Without inflation, the universe as we know it wouldn't exist. It's the reason why the cosmos looks so uniform on large scales, with galaxies spread out in every direction. Cosmic inflation also helps explain some of the biggest questions in physics, like why the universe is so finely tuned for life. Tiny fluctuations during this rapid expansion eventually grew into the galaxies and stars we see today. It's as if the universe was stretching its canvas, creating the perfect conditions for complexity to emerge. But inflation isn't just a theory. It's supported by observations of the cosmic microwave background, the faint afterglow of the Big Bang that still permeates the universe. So, what does this mean for space-time? The Big Bang and cosmic inflation remind us that space-time isn't a static backdrop. It's a dynamic, evolving entity that's been shaped by the forces of the universe since the very beginning. And as we'll see next, this evolution didn't stop with the Big Bang. The universe has been stretching, bending, and reshaping space-time ever since, creating the cosmic tapestry we see today. But how does this ongoing expansion affect the future of the universe? That's where the story gets even more intriguing. Now, let's zoom in on one of the most dramatic moments in the history of the universe: cosmic inflation. Picture this: less than a trillionth of a second after the Big Bang, the universe underwent an explosive growth spurt, expanding faster than the speed of light. This wasn't just a gentle stretching, it was a colossal burst that doubled the size of the universe over and over again in the blink of an eye. To put it into perspective, imagine blowing up a balloon to the size of the Earth and then instantly inflating it to the size of the observable universe. That's the scale of cosmic inflation, and it's the reason why space-time looks the way it does today. But why did this happen? Cosmic inflation solves some of the biggest puzzles in cosmology. For starters, it explains why the universe looks so uniform on large scales. No matter where you look, galaxies are spread out in every direction, with a remarkable consistency in temperature and density. Without inflation, this uniformity would be almost impossible to explain. It's like stirring a pot of soup until it's perfectly smooth. Cosmic inflation did the stirring for the universe, smoothing out any irregularities and creating the even distribution we see today. Another mystery inflation helps solve is the flatness of the universe. When we measure the curvature of space-time on a cosmic scale, it appears almost perfectly flat. This is surprising because without inflation, the universe would have had to start with an impossibly precise balance of energy and expansion to achieve this flatness. Inflation acts like a cosmic reset button, stretching space-time so much that any initial curvature becomes negligible, leaving the universe flat and uniform. And then there's the horizon problem. If you look at opposite ends of the observable universe, the regions are so far apart that light hasn't had enough time to travel between them since the Big Bang. Yet, these regions have nearly identical temperatures and properties. How is this possible? Inflation provides the answer. Before inflation, these regions were close enough to interact and reach equilibrium. Then, inflation stretched them apart, preserving their uniformity even as they moved far beyond each other's reach. So, what does this mean for space-time? Cosmic inflation wasn't just a one-time event, it left an indelible mark on the fabric of the universe. The rapid expansion imprinted tiny fluctuations in density, which later grew into the galaxies, stars, and planets we see today. It's like stretching a piece of fabric and creating ripples that eventually form patterns. These patterns are still visible in the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe. And speaking of the cosmic microwave background, it's time to explore how this ancient light holds the secrets to the universe's earliest moments. The cosmic microwave background, or CMB, is like a time capsule from the dawn of the universe. It's the oldest light we can see, a faint glow that fills the entire cosmos, and it holds the secrets of how space-time began. Imagine taking a photograph of the universe when it was just 380,000 years old, a baby picture of reality itself. That's essentially what the CMB is. It's the afterglow of the Big Bang, the moment when the universe cooled enough for light to travel freely for the first time. Before that, the cosmos was a hot, dense soup of particles, too chaotic for light to escape. But as the universe expanded and cooled, it became transparent, and that first burst of light has been traveling through space ever since, carrying with it a snapshot of the early universe. What makes the CMB so special is that it's not just ancient light, it's a map of the early structure of space-time. When scientists study the CMB, they're looking at tiny fluctuations in temperature, variations so small they're measured in millionths of a degree. These fluctuations are like cosmic fingerprints, imprinted by the quantum foam of the early universe. They reveal the seeds of everything we see today, the galaxies, stars, and planets that formed from these tiny ripples in space-time. It's as if the universe left us a blueprint showing how it grew from a hot, dense state into the vast, intricate cosmos we inhabit. But the CMB isn't just a relic of the past, it's also a tool for understanding the present and future of the universe. By studying its patterns, scientists have confirmed key predictions of the Big Bang theory, like the age of the universe and the amount of dark matter and dark energy it contains. It's like having a Rosetta Stone for cosmology, helping us decode the mysteries of space-time. And yet, for all we've learned, the CMB still holds unanswered questions. Why, for example, does it show a slight asymmetry in temperature between one side of the universe and the other? Could this be a clue to something even bigger, like the existence of other universes beyond our own? This brings us to one of the most mind-bending ideas in modern physics, the multiverse. If the CMB is a snapshot of our universe's infancy, could there be other snapshots out there, each representing a different universe with its own unique laws of physics? The idea of a multiverse takes the concept of space-time to a whole new level, suggesting that what we see as the universe might just be one small piece of a much larger, more complex reality. But how could we ever prove such a thing? That's where the next fact takes us, into the realm of parallel universes and the tantalizing possibility that our universe is just one of many. What if our universe isn't the only one out there? What if, beyond the boundaries of space and time as we know it, there are countless other universes, each with its own unique set of physical laws and dimensions? This isn't just a wild idea from science fiction. It's a serious scientific hypothesis known as the Multiverse Theory. According to this theory, our universe might be just one bubble in a vast cosmic foam, with each bubble representing a separate universe, complete with its own space-time fabric. It's a concept that stretches the imagination, but it's rooted in some of the most advanced theories in physics, from quantum mechanics to string theory. So, how could multiple universes exist? One of the leading ideas comes from cosmic inflation, the rapid expansion of the early universe we discussed earlier. During inflation, tiny quantum fluctuations could have caused different regions of space-time to expand at different rates, creating pocket universes that are disconnected from one another. Each of these universes could have its own unique properties. Different constants of nature, different physical laws, even different numbers of dimensions. It's like a cosmic lottery where every universe gets its own set of rules, and ours just happens to be the one where life can exist. But the multiverse isn't just a theoretical playground, it's also a potential solution to some of the biggest mysteries in physics. For example, why do the fundamental constants of nature, like the speed of light or the strength of gravity, have the precise values they do? If there are countless universes, each with different constants, it's not surprising that at least one would have the right conditions for life. This idea, known as the Anthropic Principle, suggests that we observe the universe the way it is because it's the only one where we could exist to observe it. It's a humbling thought, but it also opens the door to a universe or multiverse of possibilities. Now, here's where it gets even more intriguing. Some versions of the multiverse theory suggest that these parallel universes aren't just disconnected bubbles. They could be interacting with each other in subtle ways. For instance, collisions between universes might leave imprints in the cosmic microwave background, the ancient light we talked about earlier. While we haven't found definitive evidence of such collisions yet, the search is ongoing and the implications are staggering. If we could detect signs of another universe, it would revolutionize our understanding of reality itself. But the multiverse isn't just about physics, it's also a philosophical challenge. If there are infinite universes, does that mean every possible version of reality exists somewhere? Could there be a universe where dinosaurs never went extinct, or where you made a different choice at a pivotal moment in your life? These questions blur the line between science and speculation, but they also highlight the profound mystery of existence. The multiverse theory reminds us that the universe, or universes, are far stranger and more complex than we can imagine. And speaking of complexity, this idea of multiple space-times raises another fascinating question. Could we ever travel between universes? While it's a tantalizing thought, the practical challenges are immense. The laws of physics as we know them would likely prevent such a journey, but that hasn't stopped scientists from exploring the possibilities. Some theories suggest that wormholes, those hypothetical tunnels through space-time, could connect different universes. Others propose that quantum entanglement, the strange phenomenon where particles can influence each other across vast distances, might offer a glimpse into parallel realities. While these ideas remain speculative, they're a testament to the boundless curiosity that drives our exploration of the cosmos. So, what does the multiverse mean for our understanding of space-time? It's a reminder that the fabric of reality might be far more intricate than we've ever imagined. Whether or not we ever find proof of other universes, the multiverse theory challenges us to think bigger, to consider that our universe might be just one thread in an infinite cosmic tapestry. And as we continue to explore the mysteries of space-time, who knows what other astonishing truths we might uncover? What if the laws of physics weren't universal? What if, in another universe, space-time behaved in ways we can't even imagine? This is the tantalizing idea behind parallel universes, a concept that suggests our universe might be just one of many, each with its own unique set of rules. In some of these universes, space-time could be completely different. Imagine a universe where time flows backward, or where gravity is so weak that planets never form. In another, space might have more than 3 dimensions, creating a reality where up, down, left, and right aren't the only directions you can move. These aren't just wild ideas, they're possibilities that emerge from some of the most advanced theories in physics, like string theory and quantum mechanics. To get a sense of how this might work, let's take a thought experiment. Picture a universe where the speed of light isn't a constant. In our universe, light speed is the ultimate limit, shaping everything from causality to the structure of space-time. But in this parallel universe, light could travel faster or slower, completely altering how time and space interact. Events that are simultaneous here might happen in a different order there. Or consider a universe where time isn't linear at all. Instead of flowing in one direction, it might loop back on itself, creating endless cycles of cause and effect. These variations aren't just theoretical, they're a reminder of how finely tuned our own universe seems to be. But why would space-time laws differ in other universes? One explanation comes from the idea of cosmic inflation. During the rapid expansion of the early universe, different regions of space-time could have frozen into different states, each with its own physical constants. It's like a cosmic patchwork quilt, where each patch represents a universe with its own unique rules. Some of these universes might be so alien that life as we know it couldn't exist there. Others might be eerily similar to ours with only subtle differences. The possibilities are as vast as the multiverse itself. Now, here's where it gets even more intriguing. If parallel universes exist, could we ever detect them? Some scientists believe that collisions between universes might leave faint imprints in the cosmic microwave background, the ancient light we talked about earlier. While we haven't found definitive evidence yet, the search is ongoing and the implications are staggering. Discovering another universe would not only confirm the multiverse theory, but also revolutionize our understanding of reality itself. This idea of multiple space-times raises a fascinating question. Could we ever travel to another universe? While it's a thrilling thought, the practical challenges are immense. The laws of physics as we know them would likely prevent such a journey, but that hasn't stopped scientists from exploring the possibilities. Some theories suggest that wormholes, those hypothetical tunnels through space-time, could connect different universes. Others propose that quantum entanglement, the strange phenomenon where particles can influence each other across vast distances, might offer a glimpse into parallel realities. While these ideas remain speculative, they're a testament to the boundless curiosity that drives our exploration of the cosmos. And speaking of exploration, this brings us to another mind-bending concept: time travel. If space-time can vary so dramatically across universes, what does that mean for our ability to move through time? Could the rules of time travel be different in other realities, or is there a universal principle that governs it all? That's where our next fact takes us, into the realm of time loops, paradoxes, and the tantalizing possibility of bending time itself. What if time travel isn't just a fantasy but a real possibility hidden within the fabric of space-time? Enter the concept of closed time-like curves, or CTC, a theoretical pathway through space-time that could, in theory, allow you to loop back to your own past. Imagine drawing a circle on a piece of paper where the end of the line connects back to the beginning. A closed time-like curve works similarly, creating a loop in space-time that could let you travel back to a previous moment. It's a mind-bending idea that comes straight from Einstein's equations of general relativity, and it's one of the most intriguing possibilities in modern physics. But how could such a loop exist? One way is through the extreme warping of space-time, like near a rotating black hole. Known as a Kerr black hole, this type of black hole spins so fast that it drags space-time around with it, creating a whirlpool-like effect. If you were to orbit close enough to the black hole, you might find yourself on a path that loops back in time. It's like running on a treadmill that's moving faster than you, except instead of staying in place, you're traveling through time. While this sounds like the stuff of science fiction, it's a mathematically valid solution to Einstein's equations. The catch: you'd need to survive the intense gravitational forces and radiation near the black hole, which is no small feat. Even if we could navigate these challenges, time travel through CTCs comes with its own set of paradoxes. The most famous is the grandfather paradox. What if you traveled back in time and prevented your own birth? If you were never born, how could you have traveled back in time to begin with? This paradox highlights the logical inconsistencies that arise when we try to bend the rules of causality. Some physicists suggest that the universe might prevent such paradoxes by self-correcting, ensuring that any actions you take in the past align with the timeline you came from. Others propose that time travel might only be possible in parallel universes, where your actions create a new timeline instead of altering your own. But the challenges don't stop there. Even if closed time-like curves exist, they might be incredibly unstable. Quantum effects, like the buildup of energy in a loop, could make them collapse before anyone could use them. It's like trying to build a bridge out of sand. It might look solid at first, but it could crumble under the slightest pressure. These hurdles make time travel through CTCs a tantalizing but uncertain possibility, one that continues to spark debate among scientists. So, what does this mean for our understanding of time? Closed time-like curves remind us that time isn't as straightforward as it seems. It's not just a one-way street. Under the right conditions, it might loop back on itself, creating opportunities for travel that defy our everyday experience. But as we explore these possibilities, we're also forced to confront the fundamental nature of time itself. Why does it seem to flow in one direction? That's where our next fact takes us, into the mystery of the arrow of time and why the past feels so different from the future. Why does time always seem to flow forward like a river that never runs backward? This is the mystery of the arrow of time, a fundamental feature of our universe that shapes everything from the growth of trees to the aging of stars. Unlike space, where we can move in any direction, time appears to have a one-way street. But why is this the case? The answer lies in a concept called entropy, a measure of disorder in the universe. According to the second law of thermodynamics, entropy always increases over time. Think of it like a deck of cards. If you shuffle it, the cards become more disordered, and it's highly unlikely they'll ever return to their original ordered state. This tendency toward disorder is what gives time its direction, creating a clear distinction between the past and the future. But here's where it gets even more fascinating. While entropy explains why time flows forward, it doesn't tell us why the universe started in such an ordered state to begin with. Some scientists believe this might be linked to the Big Bang, when the universe was incredibly hot and dense, with entropy at its lowest point. As the universe expanded and cooled, entropy began to increase, setting the arrow of time in motion. It's as if the Big Bang wound up the cosmic clock, and we've been ticking forward ever since. This idea not only explains why time moves in one direction, but also raises questions about the ultimate fate of the universe. If entropy keeps increasing, will the universe eventually reach a state of maximum disorder where nothing can happen anymore? It's a chilling thought, but it's also a reminder of how deeply connected time is to the very fabric of reality. Now, let's take this idea a step further. While entropy drives the arrow of time in our everyday experience, scientists have discovered something that seems to defy this rule: time crystals. These aren't crystals in the traditional sense. They're a new phase of matter that repeats its structure not in space but in time. Imagine a clock that ticks forever without any energy input, or a dance that repeats itself endlessly without anyone leading it. That's the essence of a time crystal. Unlike everything else in the universe which tends toward disorder, time crystals maintain a stable, repeating pattern over time, almost as if they've found a way to sidestep the arrow of time. So, what does this mean for our understanding of time? Time crystals challenge the idea that entropy always increases, suggesting that under certain conditions, order can persist indefinitely. While they don't break the laws of thermodynamics, they still require energy to form. They do open up new possibilities for how we think about time and order in the universe. Could time crystals hold the key to new technologies like quantum computers that operate with incredible efficiency? Or do they hint at deeper truths about the nature of time itself? These questions are still being explored, but one thing is clear: the arrow of time isn't as straightforward as it seems. And as we'll see next, this complexity extends even further when we consider the role of time in the quantum realm. Now, let's dive into one of the most mind-bending discoveries in modern physics: time crystals. These aren't your ordinary crystals like quartz or diamond. They're a completely new state of matter that defies our traditional understanding of time. While regular crystals have a repeating structure in space, like the symmetrical patterns of a snowflake, time crystals repeat their structure in time. Imagine a clock that ticks endlessly without any external energy, or a dance that loops perfectly without anyone leading it. That's the essence of a time crystal, a system that maintains a stable, repeating pattern over time, almost as if it's found a way to cheat the arrow of time. So, how do time crystals work? At their core, they rely on a phenomenon called time symmetry breaking. In most systems, time symmetry means that the laws of physics work the same way whether time moves forward or backward. But time crystals break this symmetry by creating a pattern that repeats at regular intervals, even though the system itself doesn't gain or lose energy. It's like a pendulum that swings back and forth forever without any friction or external push. This behavior is so unusual that it challenges some of our most fundamental ideas about how matter and energy behave. The discovery of time crystals has opened up exciting possibilities for physics and technology. For one, they could revolutionize quantum computing. Because time crystals maintain their stability over time, they might be used to create quantum systems that are far more robust and efficient than anything we have today. Imagine a quantum computer that doesn't lose information over time. Time crystals could make that a reality. But beyond practical applications, time crystals also force us to rethink the nature of time itself. If a system can repeat its structure indefinitely, does that mean time isn't as linear as we thought? Could there be other states of matter that behave in similarly strange ways? These are questions that scientists are still exploring, and the answers could reshape our understanding of the universe. But time crystals aren't the only thing bending the rules of physics. Just as they challenge our ideas about time, another phenomenon is shaking up our understanding of space: gravitational waves. These ripples in the fabric of space-time, first predicted by Einstein over a century ago, were finally detected in 2015, opening a whole new window into the cosmos. What are gravitational waves, and how do they reveal the hidden workings of the universe? That's where our next fact takes us, into the heart of one of the most groundbreaking discoveries in modern astronomy. Gravitational waves are like cosmic echoes rippling through the fabric of space-time itself. These waves are created by some of the most violent and energetic events in the universe, colliding black holes, merging neutron stars, or even the explosive birth of the universe during the Big Bang. Imagine dropping a pebble into a still pond and watching the ripples spread outward. Gravitational waves work in a similar way, except instead of water, they distort the very fabric of reality, stretching and squeezing space-time as they travel across the cosmos. The existence of gravitational waves was first predicted by Albert Einstein over a century ago as part of his theory of general relativity. But it wasn't until September 2015 that scientists made the first direct detection using the Laser Interferometer Gravitational Wave Observatory, or LIGO. The discovery was monumental, a confirmation of Einstein's theory and a new way to observe the universe. The waves detected came from the collision of two black holes over 1 billion light-years away, an event so powerful that it sent ripples through space-time that we could measure here on Earth. It's like hearing the universe itself speak, revealing secrets that light alone could never show. What makes gravitational waves so groundbreaking is that they allow us to listen to the universe in a completely new way. Traditional telescopes rely on light, but gravitational waves are unaffected by dust, gas, or other obstacles that might block our view. They give us a direct window into the most extreme environments, like the hearts of black holes or the cores of neutron stars. Since that first detection, scientists have observed dozens of gravitational wave events, each one adding to our understanding of the cosmos. It's as if we've been given a new sense, allowing us to explore the universe in ways we never thought possible. But gravitational waves aren't just about observing distant events, they also provide clues about the nature of space-time itself. When two black holes collide, for example, the resulting gravitational waves carry information about the shape and behavior of space-time in the most extreme conditions. These observations have already challenged some of our assumptions, like the exact nature of black hole horizons or the limits of Einstein's theory. And as our detectors become more sensitive, we'll be able to probe even deeper into the mysteries of the universe, from the earliest moments after the Big Bang to the potential existence of exotic objects like wormholes. This brings us to another mind-bending idea, the holographic principle. If gravitational waves reveal the dynamic nature of space-time, could it be that space-time itself is more like a projection, a hologram of a deeper, more fundamental reality? This isn't just a wild thought experiment. It's a serious scientific hypothesis that could reshape our understanding of the universe. And that's where our next fact takes us, into the realm of holograms, information, and the possibility that everything we see might just be a cosmic illusion. What if everything we see, touch, and experience is just a projection, a cosmic hologram? This is the mind-bending idea behind the holographic principle, a theory that suggests our three-dimensional reality might be encoded on a two-dimensional surface, like a movie projected onto a screen. At first glance, it sounds like science fiction, but this concept has deep roots in physics, particularly in the study of black holes and quantum mechanics. The holographic principle challenges our most basic assumptions about space and time, proposing that the universe might not be as three-dimensional as it seems. Instead, all the information about the cosmos, every star, planet, and galaxy, could be stored on a vast two-dimensional boundary like the surface of a bubble. It's a radical idea, but one that could revolutionize our understanding of reality. So, how does this work? Let's start with black holes, where the holographic principle first gained traction. When an object falls into a black hole, it seems to disappear forever. But according to the laws of quantum mechanics, information can never be truly lost. This creates a paradox. How can the information about the object be preserved if it's trapped inside the black hole? The holographic principle offers a solution. It suggests that all the information about the object is encoded on the black hole's event horizon, the boundary beyond which nothing can escape. In other words, the three-dimensional object is projected onto a two-dimensional surface, preserving its information in a way that doesn't violate the laws of physics. This idea isn't just limited to black holes. Some physicists believe the entire universe might work the same way, with our three-dimensional reality being a projection of information stored on a two-dimensional surface at the edge of the cosmos. But what does this mean for space-time? If the holographic principle is correct, it implies that space-time isn't fundamental, it's an emergent property, like the image on a movie screen. The real code of the universe exists on a deeper, two-dimensional level, and what we perceive as space and time is just a projection of that information. This idea has profound implications for physics, potentially unifying quantum mechanics and general relativity, two theories that have long been at odds. It also raises fascinating questions about the nature of reality. If space-time is a projection, could we one day decode the underlying information and manipulate it? Could we rewrite the universe like editing a film? While these questions remain speculative, they highlight the transformative potential of the holographic principle. Now, here's where things get even more intriguing. The holographic principle isn't just about space-time. It's also deeply connected to another mysterious phenomenon, quantum entanglement. This is the strange phenomenon where two particles become linked, so that the state of one instantly affects the state of the other, no matter how far apart they are. It's as if the particles are communicating faster than the speed of light, defying our everyday understanding of space and time. Some scientists believe that quantum entanglement might be the key to understanding how information is encoded on the two-dimensional surface described by the holographic principle. In other words, the entangled particles could be like pixels on a cosmic screen, storing the information that creates our three-dimensional reality. This connection between the holographic principle and quantum entanglement opens up a whole new way of thinking about the universe. It suggests that the fabric of reality might be woven together by information, with space-time emerging from the intricate web of quantum connections. It's a perspective that blurs the line between the very large and the very small, showing how the behavior of particles at the quantum level could shape the structure of the cosmos. And as we'll see next, this interplay between information, space, and time might hold the key to some of the deepest mysteries in physics, from the nature of black holes to the origins of the universe itself. Now let's dive into one of the most baffling phenomena in the quantum world, quantum entanglement. Picture this: two particles, separated by vast distances, somehow remain connected in such a way that the state of one instantly influences the state of the other. It's as if they're sharing a secret language that doesn't care about the rules of space and time. This isn't just a quirky observation. It's a fundamental feature of quantum mechanics that challenges everything we thought we knew about reality. Albert Einstein famously called it spooky action at a distance, and for good reason. It seems to defy the very fabric of space-time. Here's how it works. When two particles become entangled, they form a kind of bond that links their properties, like spin or polarization. If you measure one particle and find it spinning in a certain direction, the other particle will instantly match that spin, no matter how far apart they are. This connection happens faster than the speed of light, seemingly bypassing the limits of space-time. It's like having two coins that always land on the same side, even if one is flipped in New York and the other in Tokyo. The strangest part, this connection isn't due to any hidden signal or force traveling between them. It's just how the universe works at the quantum level. So, what does this mean for our understanding of space-time? Quantum entanglement suggests that space and time might not be as fundamental as we think. Instead of being the stage on which everything happens, space-time could be more like a projection, emerging from deeper, more fundamental connections between particles. It's as if the universe is playing a cosmic game of chess, where the pieces are entangled in ways that transcend the board itself. This idea has profound implications, not just for physics, but for how we see reality. Could space-time be an illusion, a byproduct of quantum interactions we're only beginning to understand? The implications of quantum entanglement go even further. Some scientists believe it could be the key to unlocking new technologies, like quantum computers that perform calculations at unimaginable speeds. Others see it as a clue to the nature of the universe itself, suggesting that everything might be interconnected in ways we can't yet fully grasp. It's a reminder that the quantum world is full of surprises, constantly challenging our assumptions and pushing the boundaries of what we think is possible. But quantum entanglement isn't just about particles, it's also deeply connected to the nature of time. If entangled particles can communicate instantaneously, does that mean time itself works differently at the quantum level? This brings us to our next mind-bending fact, the possibility that time might not flow in a straight line, but could instead loop, twist, or even branch into multiple paths. What if the arrow of time isn't as straightforward as it seems? That's where the story gets even more intriguing. What if time isn't real? What if the ticking of clocks and the passing of days are just illusions, a kind of cosmic trick our brains play on us? This might sound like the plot of a sci-fi movie, but it's a serious idea in modern physics. Some scientists argue that time isn't a fundamental part of the universe. It's something that emerges from deeper, more basic processes. Think of it like a movie. What we see on the screen isn't the film itself, but a projection of it. In the same way, time might be a projection of something more fundamental, a way for the universe to organize and make sense of itself. One of the leading theories challenging our perception of time comes from quantum mechanics. At the smallest scales, particles don't behave in a linear cause and effect way. Instead, they exist in a state of probability where events don't happen in a strict sequence. This has led some physicists to suggest that time might not flow at all. It could be more like a collection of moments, all existing simultaneously. It's as if the universe is a giant photo album, and time is just the order in which we flip through the pages. But in reality, all the photos are already there, waiting to be seen. Another fascinating idea comes from the study of black holes. Near a black hole's event horizon, time appears to slow down dramatically, almost as if it's freezing. But from the perspective of someone falling into the black hole, time feels normal. This discrepancy suggests that time might not be an absolute, universal constant, but something that depends on your perspective and the conditions around you. It's like standing in a river. The water might flow faster in some places and slower in others, but the river itself is still the same. Time, in this view, is more fluid than we realize. So, if time isn't fundamental, what does that mean for our understanding of reality? It opens up the possibility that space-time itself might not be the ultimate framework of the universe. Instead, it could be a kind of emergent structure built from something even more basic like information or quantum interactions. This idea is still in its early stages, but it's already reshaping how we think about the cosmos. And as we'll see next, this rethinking of time also ties into the shape of space-time itself, a concept that's just as mind-bending as the idea of time being an illusion. What if the shape of the universe isn't what you think it is? Space-time, the fabric that holds everything together, might not be flat like a tabletop. It could be curved, open, or even closed like the surface of a sphere. These three possible geometries aren't just abstract ideas. They determine the ultimate fate of the universe itself. Let's break it down. First, there's flat space-time, which is exactly what it sounds like, a universe where parallel lines stay parallel forever, and the rules of geometry work just like they do in high school math class. In a flat universe, space-time stretches out infinitely in all directions, and the cosmos will keep expanding forever, though at a slower and slower rate over time. Now, imagine space-time as the surface of a sphere. This is the closed universe model. In this scenario, the universe is finite but has no edges, much like how you can travel around the Earth without ever falling off. If you were to travel in a straight line in a closed universe, you'd eventually end up back where you started. But here's the twist. A closed universe would eventually stop expanding and collapse back in on itself in a dramatic event called the Big Crunch. It's like the universe taking a deep breath and then exhaling, bringing everything back to a single point. On the other hand, an open universe is like a saddle, curved in such a way that parallel lines diverge over time. In this model, space-time stretches out infinitely, and the universe expands forever, growing colder and emptier as galaxies drift farther apart. Each of these geometries, flat, closed, or open, has profound implications for the fate of the cosmos. Will the universe expand forever, collapse, or find a delicate balance? The answer lies in the shape of space-time itself. But how do we know which shape our universe has? Scientists use a variety of tools to measure the curvature of space-time, from the cosmic microwave background to the distribution of galaxies. So far, the evidence points to a flat universe, but the mystery isn't fully solved. And this is where dark matter comes into play. This invisible substance, which makes up about 27% of the universe, plays a crucial role in shaping the geometry of space-time. Without dark matter, galaxies wouldn't hold together and the universe might look very different. But what exactly is dark matter and how does it influence the cosmos? That's where our next fact takes us, into the shadowy realm of one of the universe's greatest mysteries. Dark matter might be invisible, but its influence on the universe is anything but subtle. This mysterious substance, which makes up about 27% of the cosmos, doesn't emit, absorb, or reflect light, making it impossible to see directly. Yet, its gravitational pull is so powerful that it shapes the very structure of space-time itself. Think of dark matter as the cosmic scaffolding that holds galaxies together and guides their movements. Without it, the universe as we know it would look completely different. Galaxies would fly apart, and the intricate web of cosmic structures we see today wouldn't exist. So how does dark matter bend space-time? It all comes down to gravity. Just like stars and planets, dark matter exerts a gravitational force, creating dips and curves in the fabric of space-time. These distortions aren't just local, they stretch across vast distances, influencing the motion of galaxies and even the paths of light itself. This effect, known as gravitational lensing, allows scientists to map the distribution of dark matter by observing how it bends the light from distant objects. It's like seeing the shadow of something invisible, revealing its presence through the way it warps the world around it. But dark matter's role goes beyond just bending light. It's also the architect of the cosmic web, the vast network of filaments that connects galaxies across the universe. These filaments are like the threads of a spider's web, with dark matter acting as the glue that holds everything together. Galaxies form at the intersections of these filaments, drawn together by the gravitational pull of dark matter. It's a cosmic dance choreographed by an invisible force that we're only beginning to understand. Now, here's where it gets even more intriguing. While dark matter shapes the large-scale structure of the universe, it also raises questions about the nature of space-time itself. Could dark matter be influencing the curvature of the universe on a grand scale, determining whether space-time is flat, open, or closed? Some scientists believe that dark matter, along with dark energy, holds the key to understanding the ultimate fate of the cosmos. Will the universe keep expanding forever, or will it eventually collapse back in on itself? The answer might lie in the invisible hand of dark matter. But dark matter isn't just a cosmic mystery, it's also a reminder of how much we still have to learn about the universe. Despite decades of research, we've yet to directly detect dark matter particles or fully understand their properties. It's a puzzle that challenges our most fundamental theories, from gravity to particle physics. And as we continue to explore, we're uncovering new clues that could reshape our understanding of space-time and the forces that govern it. Speaking of cosmic structures, this brings us to the next mind-blowing fact: the cosmic web. If dark matter is the scaffolding, the cosmic web is the masterpiece it supports. A vast, interconnected network of galaxies, gas, and dark matter that spans the entire universe. What is the cosmic web and how does it shape the cosmos? That's where we're headed next, into the heart of one of the most awe-inspiring structures in existence. The universe isn't just a random scattering of galaxies, it's a meticulously organized masterpiece, connected by an intricate network known as the cosmic web. Picture this: galaxies aren't floating alone in the void. They're strung together like beads on invisible threads, woven into a vast, sprawling tapestry that stretches across the cosmos. These threads are made of dark matter, the mysterious substance we can't see but whose gravitational pull shapes everything around it. The cosmic web is the backbone of the universe, a structure so immense that it connects galaxies across billions of light years, forming a web of filaments, nodes, and voids that define the large-scale structure of space-time. At the heart of this cosmic web are the filaments, long, thin strands of dark matter that act like highways for galaxies. These filaments intersect at dense nodes where galaxies cluster together in massive groups, creating the brightest and most active regions of the universe. Between the filaments lie vast, empty voids, regions of space where matter is sparse and galaxies are few and far between. It's a bit like looking at a sponge. The holes are the voids, and the material around them forms the web. This structure isn't just beautiful, it's essential for understanding how the universe evolved. Without the cosmic web, galaxies wouldn't have the gravitational scaffolding they need to form and grow. It's the reason we see galaxies grouped together in clusters and superclusters, rather than scattered randomly across the cosmos. But how did this web come to be? It all traces back to the early universe, just moments after the Big Bang. Tiny fluctuations in density, imprinted in the cosmic microwave background, grew over billions of years, pulled together by gravity. Dark matter, with its invisible but powerful gravitational influence, acted as the cosmic glue, drawing matter into filaments and nodes. Ordinary matter, the stuff we can see, like stars and gas, followed this dark matter blueprint, condensing into galaxies along the web structure. It's a process that's still happening today as the cosmic web continues to evolve, shaping the universe on the largest scales. The cosmic web isn't just a static structure, it's a dynamic, ever-changing network. Galaxies move along the filaments, pulled by gravity toward the densest nodes where they collide and merge, forming even larger galaxies. Meanwhile, the voids between the filaments grow larger as the universe expands, stretching the web thinner over time. This interplay between structure and expansion is what makes the cosmic web so fascinating. It's not just a snapshot of the universe. It's a living, breathing entity that tells the story of how the cosmos grew from a hot, dense soup of particles into the vast, complex structure we see today. So, what does the cosmic web mean for the future of space-time? As the universe continues to expand, the web will stretch and thin, with galaxies drifting farther apart. But the fate of this cosmic structure isn't set in stone. It's tied to the mysterious forces of dark energy and dark matter, which shape the geometry and evolution of the universe. Will the cosmic web continue to grow, or will it eventually unravel? That's where our next fact takes us, into the ultimate fate of space-time and the forces that will determine how the universe ends. Now, let's take a journey to the far, far future, a time so distant that stars have burned out, galaxies have faded, and the universe itself has reached its final state. This is the heat death of the universe, a scenario where space-time itself could lose all structure and meaning. It's a chilling thought, but one rooted in the laws of thermodynamics. Over trillions upon trillions of years, the universe will continue to expand, driven by dark energy, until all usable energy is exhausted. Stars will exhaust their fuel, black holes will evaporate, and even the protons that make up matter could decay. What's left will be a cold, dark, and featureless void, a universe where entropy or disorder has reached its maximum. In this state, space-time itself could become meaningless, with no events or changes to mark the passage of time. It's as if the universe has run out of stories to tell, leaving behind only silence. But here's where the story takes an intriguing turn. While the heat death of the universe might seem like the ultimate end, some scientists propose an alternative, the idea of a cyclic universe. Imagine the universe not as a one-time event, but as part of an endless cycle of birth, death, and rebirth. In this model, the heat death isn't the end, it's just a pause before the next Big Bang. The idea is that after trillions of years, the universe could somehow reset, collapsing back into a singularity and sparking a new cycle of expansion. It's like a cosmic phoenix rising from the ashes of its own demise. While this remains speculative, it offers a glimmer of hope that the universe might not end in eternal stillness, but could instead be part of an infinite loop of creation and destruction. This concept of a cyclic universe ties back to the nature of space-time itself. If the universe can collapse and expand again, it suggests that space-time isn't a fixed stage but a dynamic, evolving entity. It's a reminder that even in the face of entropy, the cosmos might have a way of reinventing itself. Whether the universe ends in heat, death, or cycles endlessly, one thing is clear: the story of space-time is far from over. And as we explore these possibilities, we're reminded of just how vast, mysterious, and awe-inspiring the cosmos truly is. What if the universe isn't a one-time event but part of an endless loop, like a cosmic heartbeat? This is the idea behind cyclic universes, a theory that suggests space-time itself might repeat in an infinite cycle of expansion and contraction. Instead of a single Big Bang leading to a final heat death, the universe could collapse back into a singularity, only to explode outward again in a new Big Bang. It's a concept that turns our understanding of space-time on its head, proposing that the fabric of reality isn't linear but cyclical, like a cosmic dance that never ends. So how does this work? Imagine the universe as a balloon. In the cyclic model, the balloon inflates, expands to its limit, and then deflates only to inflate again. Each cycle begins with a Big Bang, followed by billions of years of expansion, and eventually ends with a big crunch where everything collapses back into a single point. This process could repeat endlessly, with space-time stretching and contracting in an eternal rhythm. It's a vision of the cosmos that's both awe-inspiring and humbling, suggesting that the universe we know might be just one chapter in an infinite story. But what does this mean for space-time? If the universe cycles endlessly, space-time itself becomes a dynamic, evolving entity. Instead of being a fixed stage, it's more like a living, breathing organism, constantly reshaping itself. Each cycle could leave behind traces of the previous one, like cosmic echoes imprinted in the fabric of reality. Some scientists even speculate that these echoes might be detectable, offering clues about the universe's past and future cycles. It's a tantalizing possibility that could reshape our understanding of time, space, and the very nature of existence. Now, here's where it gets even more intriguing. If the universe is cyclical, what happens to the laws of physics in each new cycle? Could they change, creating a universe with entirely different rules? Some theories suggest that each cycle might reset the constants of nature, like the speed of light or the strength of gravity, leading to a universe that's subtly or dramatically different from the one before. It's a reminder that space-time isn't just a backdrop, it's an active participant in the cosmic drama, shaping the rules of reality itself. But cyclic universes aren't just about space-time, they also raise profound questions about the nature of existence. If the universe repeats itself, does that mean everything that's ever happened will happen again? Could there be infinite versions of you, living out infinite variations of your life in each new cycle? These questions blur the line between science and philosophy, challenging us to think beyond the limits of our current understanding. As we ponder the possibility of a cyclical universe, it's worth considering another mind-bending idea: the role of consciousness in shaping reality. Could our awareness of the universe somehow influence its structure or even its cycles? That's where our next fact takes us, into the mysterious interplay between space-time and the human mind. What if consciousness isn't just a product of the brain, but something woven into the very fabric of space-time? This might sound like the plot of a sci-fi novel, but it's a question that's been explored by both physicists and philosophers. Some theories suggest that consciousness could be a fundamental aspect of the universe, as essential as space and time themselves. Imagine if the act of observing the world doesn't just happen within space-time, but actually influences it. This idea, while speculative, challenges our understanding of reality and raises profound questions about the nature of existence. One of the most intriguing theories comes from quantum mechanics, where the act of observation seems to play a crucial role in determining the state of particles. In the famous double-slit experiment, particles behave differently when they're being observed, almost as if they know they're being watched. This has led some scientists to propose that consciousness might be a key factor in shaping reality at the quantum level. It's as if the universe is a participatory experience where observers and the observed are deeply intertwined. While this idea is far from proven, it opens the door to a radical rethinking of how space-time and consciousness might be connected. But the connection between consciousness and space-time doesn't stop at quantum mechanics. Some philosophers and physicists have suggested that consciousness could be a property of the universe itself, like gravity or electromagnetism. In this view, the universe isn't just a collection of matter and energy. It's a living, conscious entity, and space-time is the medium through which this consciousness operates. It's a perspective that blurs the line between science and spirituality, suggesting that the cosmos might be more alive and interconnected than we've ever imagined. Now, here's where it gets even more fascinating. If consciousness is linked to space-time, could it influence the structure of reality on a larger scale? Some speculative theories propose that collective human consciousness might shape the evolution of the universe, guiding its development in ways we can't yet comprehend. It's a bold idea, one that challenges us to think beyond the limits of our current understanding, but it also raises questions about the limits of human knowledge. How much of the universe can we truly grasp, and are there aspects of reality that will always remain beyond our reach? This brings us to the next mind-bending fact: the limits of human understanding. As we've seen, space-time is full of mysteries that push the boundaries of science and philosophy. From the quantum realm to the cosmic web, the universe constantly challenges us to rethink what we know. But what happens when we reach the edge of what we can comprehend? That's where the story gets even more intriguing. As much as we've uncovered about space-time, from its warping near black holes to its intricate connection with quantum mechanics, there's still so much we don't know. Despite centuries of scientific progress, space-time remains one of the greatest mysteries in the universe. For every question we answer, a dozen more arise, each more perplexing than the last. Why does dark energy accelerate the expansion of the universe? What happens to space-time inside a black hole's singularity? And how do the rules of quantum mechanics, which govern the smallest particles, fit with the vast, smooth fabric of space-time described by general relativity? These are just a few of the puzzles that keep scientists up at night, reminding us that our understanding of the cosmos is still a work in progress. The beauty of science lies in its ability to evolve. Every discovery, no matter how small, adds a new piece to the cosmic puzzle. Take gravitational waves, for example. Predicted by Einstein over a century ago, they weren't detected until 2015, opening a whole new way to observe the universe. Similarly, the discovery of dark matter and dark energy completely reshaped our understanding of the cosmos, showing us that the visible universe is just the tip of the iceberg. These breakthroughs remind us that space-time isn't just a static concept, it's a dynamic field of study, constantly revealing new layers of complexity and wonder. But the journey isn't just about filling in the gaps, it's about asking the right questions and being open to the possibility that our current theories might one day be overturned. After all, Einstein's theory of relativity revolutionized physics, but it didn't erase Newton's laws, it built upon them. In the same way, future discoveries about space-time might challenge what we think we know, leading to even deeper insights. The universe is full of surprises, and space-time is no exception. Whether it's the nature of quantum gravity, the true shape of the universe, or the ultimate fate of space-time itself, there's no shortage of mysteries waiting to be solved. And that's what makes the study of space-time so thrilling. It's not just about understanding the universe, it's about embracing the unknown, the questions we can't yet answer. It's about looking at the night sky and realizing that every star, every galaxy, is part of a vast, interconnected tapestry that we're only beginning to unravel. The more we learn, the more we realize how much there is still to discover. And that brings us to our final fact, one that ties everything together: the sheer beauty of space-time. It's not just a scientific concept, it's a testament to the elegance and complexity of the cosmos, a reminder that the universe is as beautiful as it is mysterious. Space-time is more than just a scientific concept, it's a breathtaking tapestry woven from the threads of the universe itself. From the warping of gravity near black holes to the delicate dance of quantum particles, space-time is the stage on which the cosmos performs its grandest act. It's a reminder that the universe isn't just a collection of stars and planets. It's a living, evolving entity shaped by forces we're only beginning to understand. Every ripple in space-time, every twist in its fabric tells a story of creation, destruction, and the endless dance of matter and energy. As we've journeyed through these 30 mind-blowing facts, we've seen how space-time bends, stretches, and even loops back on itself. We've explored the strange effects of time dilation, the mind-bending possibilities of wormholes, and the mysterious forces of dark matter and dark energy. We've peered into the quantum realm where space-time becomes a frothy sea of uncertainty, and gazed at the cosmic web, a vast network that connects galaxies across the universe. Each fact has revealed a new layer of complexity, a new mystery waiting to be unraveled. And yet, for all we've learned, space-time remains one of the greatest enigmas in science, a puzzle that continues to challenge and inspire us. But perhaps the most remarkable thing about space-time is its sheer beauty. It's not just a framework for the universe, it's a work of art, a masterpiece of physics and mathematics. The way it curves around massive objects, the way it stretches and contracts with the expansion of the cosmos, the way it connects the smallest particles to the largest galaxies, it's a testament to the elegance and harmony of the universe. Space-time reminds us that the cosmos isn't just a place of cold, hard facts. It's a place of wonder where science and beauty intertwine. So, what's next? As we continue to explore the mysteries of space-time, we're not just uncovering the secrets of the universe, we're also discovering more about ourselves. Every breakthrough, every new insight brings us closer to understanding our place in the cosmos. Whether it's the search for gravitational waves, the quest to unravel the nature of dark energy, or the dream of one day traveling through a wormhole, the study of space-time is a journey of endless curiosity and discovery. And that's what makes it so exciting. The universe is full of surprises, and space-time is the key to unlocking them. As we wrap up this journey through 30 astonishing facts about space-time, take a moment to look up at the night sky. Every star, every galaxy is part of this incredible tapestry, a reminder of how vast and mysterious the universe truly is. Space-time isn't just a scientific concept, it's an invitation to explore, to wonder, and to dream. So keep asking questions, keep seeking answers, and never stop marveling at the beauty of the cosmos. After all, the universe is waiting, and its secrets are yours to discover. As we come to the end of this journey through the mind-bending world of space-time, let's take a moment to reflect on what we've uncovered. From the way massive objects like black holes warp the fabric of reality to the bizarre effects of time dilation that make clocks tick slower near a star, space-time is anything but ordinary. We've explored how wormholes could theoretically create shortcuts across the universe, how quantum entanglement defies our understanding of distance, and how the cosmic web connects galaxies in a vast, intricate network. Each of these facts isn't just a fascinating tidbit, but it's a window into the profound mysteries that shape our universe. What makes these discoveries so extraordinary isn't just their complexity, but the way they challenge our everyday perception of reality. Time, which feels so steady and predictable, can slow down or speed up depending on where you are or how fast you're moving. Space, which seems so vast and empty, is actually a dynamic, ever-changing fabric that bends and twists under the influence of gravity. These ideas force us to rethink what we know about the universe and our place within it. They remind us that the cosmos is far stranger and more beautiful than we could ever imagine. But for every question we answer, a dozen more arise. What lies beyond the event horizon of a black hole? Could wormholes ever become a reality? And what does the existence of dark matter and dark energy mean for the ultimate fate of the universe? These are the questions that drive scientists to keep exploring, pushing the boundaries of what we know and venturing into the unknown. They are also the questions that invite us as curious observers to marvel at the mysteries that still await discovery. As the physicist Richard Feynman once said, the most important thing is to not stop questioning. Curiosity has its own reason for existing. This sentiment captures the essence of our exploration of space-time. It's not just about finding answers, it's about embracing the wonder of the unknown, the thrill of discovery, and the endless possibilities that lie ahead. Whether you're a seasoned space enthusiast or someone just beginning to explore the cosmos, these ideas remind us that the universe is a place of infinite wonder waiting to be explored. So, what do you think? Which of these facts about space-time blew your mind the most? Do you have your own theories or questions about the cosmos? Share your thoughts in the comments below. We'd love to hear from you. And if you enjoyed this journey through the mysteries of space-time, don't forget to subscribe and hit the notification bell for more mind-expanding content. The universe is full of secrets, and together we can uncover them one astonishing fact at a time. Until next time, keep looking up, keep wondering, and never stop exploring the incredible tapestry of space-time that surrounds us. The cosmos is